Welcome to our countdown of the 5 most important theories in physics. These theories have changed our understanding of the universe and continue to be subjects of study and debate. From relativity to quantum mechanics, we will explore the ideas that have revolutionized science and our view of the cosmos. Let's get started. And don't forget to subscribe to our channel for more fascinating content about the world of science. Rank number 5. String theory. In 5th place, we have the fascinating string theory. This revolutionary theory suggests that the fundamental particles that make up our universe are not indivisible points, as previously thought, but tiny strings that vibrate in different modes. These vibrations determine the properties of the particles, such as their mass and charge. Imagine a violin string. Depending on how it vibrates, it produces different notes. Similarly, the strings in this theory vibrate in various ways to create the diverse particles we know. String theory not only redefines our understanding of fundamental particles, but also offers a possible unification of 2 pillars of modern physics: gravity and quantum mechanics. Gravity, described by Einstein's general theory of relativity, and quantum mechanics, which governs the behavior of subatomic particles, have traditionally been incompatible within a unified theoretical framework. String theory proposes that these vibrating strings can reconcile these 2 theories, suggesting that all fundamental forces and particles are manifestations of a single underlying entity. Despite its elegance and potential to revolutionize our understanding of the universe, string theory has yet to be experimentally proven. The technical and conceptual challenges of testing this theory are immense, as the proposed strings are incredibly small, far beyond the capability of our current instruments to detect them. Nevertheless, string theory remains one of the most active and exciting areas of theoretical research in physics, offering an intriguing vision of the fundamental structure of the cosmos. Position number 4. Big Bang theory. In 4th place is the Big Bang theory. This revolutionary theory describes the origin of the universe from an extremely hot and dense singularity, approximately 13.8 billion years ago. According to this theory, the universe began to expand rapidly in an event that marked the beginning of time and space as we know them. This initial expansion was so rapid that it is known as cosmic inflation, and since then, the universe has continued to expand, albeit at a slower rate. One of the main pieces of evidence supporting the Big Bang theory is the expansion of the universe. In 1929, astronomer Edwin Hubble observed that galaxies are moving away from each other, suggesting that the universe is constantly expanding. This observation is known as Hubble's law and is a fundamental pillar of modern cosmology. Additionally, the cosmic microwave background radiation, discovered in 1965 by Arno Penzias and Robert Wilson, provides a snapshot of the universe in its early moments. This radiation is a remnant of the initial heat of the Big Bang, and its existence and characteristics match theoretical predictions. Another crucial piece of evidence comes from the abundance of light elements in the universe, such as hydrogen and helium. The observed proportions of these elements match the predictions of Big Bang nucleosynthesis, the process that occurred in the first few minutes after the Big Bang and led to the formation of the first atomic nuclei. Together, these observations and discoveries have solidified the Big Bang theory as the most accepted and robust explanation for the origin and evolution of the universe. Position number 3. Theory of general relativity. In 3rd place, we have Albert Einstein's theory of general relativity. This theory revolutionized our understanding of gravity, describing it not as a force, but as a consequence of the curvature of spacetime caused by mass and energy. According to this theory, massive objects like planets and stars deform the fabric of spacetime around them, and this deformation is what we perceive as gravity. This idea was a radical shift from the Newtonian view of gravity as an invisible force acting at a distance. General relativity has been confirmed by numerous observations and experiments over the years. One of the earliest and most famous was Arthur Eddington's experiment in 1919, which observed the bending of starlight during a solar eclipse, confirming that light curves when passing near a massive object, as predicted by Einstein. Since then, the theory has passed rigorous tests, including the precision of planetary orbits, the behavior of binary pulsars, and the expansion of the universe. One of the most exciting and recent confirmations of general relativity was the detection of gravitational waves in 2015 by the LIGO Observatory. These waves are disturbances in space-time caused by violent events such as the collision of black holes. The ability to detect and study these waves opens a new window to the universe, allowing us to observe phenomena that were previously invisible. The theory of general relativity has not only transformed our understanding of gravity, but has also laid the foundation for many advances in modern physics and cosmology. Position number 2. Quantum mechanics. In second place is quantum mechanics. This theory describes the behavior of particles at very small scales, where the laws of classical physics do not apply. Unlike classical physics, which deals with macroscopic objects and their predictable movements, quantum mechanics delves into the subatomic world, where particles can exist in multiple states at once, and their positions and velocities cannot be precisely determined simultaneously. This phenomenon is known as Heisenberg's uncertainty principle. Quantum mechanics has given rise to revolutionary technologies that have transformed our daily lives. For example, transistors, which are the basis of all modern electronic devices, operate thanks to the principles of quantum mechanics. Additionally, quantum computing, an emerging technology, promises to solve complex problems much faster than classical computers by leveraging quantum superposition and entanglement. These applications not only demonstrate the theoretical importance of quantum mechanics, but also its practical impact on technology and industry. Despite its successes, quantum mechanics remains an active area of research with many unresolved questions. Scientists continue to explore the limits of this theory and seek a deeper understanding of phenomena such as quantum gravity and the unification of fundamental forces. Quantum mechanics not only challenges our intuition about how the universe works, but also opens new frontiers in science and technology, promising even more surprising discoveries in the future. Position number 1. Standard model of particle physics. In the first place, we have the standard model of particle physics. This model is a theory that describes the fundamental particles that make up the universe and the forces that govern them. With the exception of gravity, the fundamental particles include quarks, leptons, and bosons, which are the building blocks of all matter. The fundamental forces described by the Standard Model are electromagnetism, the strong nuclear interaction, and the weak nuclear interaction. These forces are mediated by exchange particles such as photons, gluons, and W and Z bosons. The Standard Model has been confirmed by numerous experiments over the decades. One of the most important milestones in its validation was the discovery of the Higgs boson in 2012, carried out at the Large Hadron Collider, LHC, at CERN. The Higgs boson is a fundamental particle that gives mass to other particles through the Higgs mechanism, a crucial missing piece in the puzzle of the Standard Model. This discovery not only confirmed the existence of the Higgs boson, but also provided strong evidence for the validity of the Standard Model as a whole. Despite its success, the Standard Model is not a complete theory. There are several unresolved questions that challenge physicists. For example, the Standard Model does not include gravity, which is described by Einstein's general theory of relativity. Additionally, it does not explain dark matter and dark energy, which make up most of the universe. It also does not address the asymmetry between matter and antimatter in the universe. These limitations suggest that there must be a more fundamental theory that we have yet to discover. However, the Standard Model remains one of the most successful and precise theories in the history of physics, providing a solid foundation for future research. And there you have it, the 5 most important theories in physics. Each of them has profoundly changed our understanding of the universe and continues to be a subject of study and fascination. These theories have not only allowed us to better understand the world around us, but have also opened doors to new questions and discoveries. Thank you for joining us on this journey through scientific knowledge, and don't forget to subscribe for more fascinating content about science.